Hey everyone. In this video, I'm going to kind of wrap up our discussion of linear regression by providing some general advice for building and comparing regression models for prediction. So on the one hand, that kind of summarizes a lot of the things that we talked about in the context of linear regression, but it's also more general advice in the sense that a lot of these kind of strategies for model building for the purpose of prediction also apply when we move on to generalized linear models, which we're going to talk about after spring break. Okay. Just as an overview, there are a couple of general principles for prediction, for model building, when the goal is prediction. And again, I want to emphasize here that the goal here is prediction, not the kind of explanation of a phenomenon or a certain causal mechanism. So we're not really that interested in interpreting a specific coefficient as some causal effect. We'll get to that after the break. But the goal here is to build a model that predicts the outcome as accurately as possible without overfitting. Okay. So the task here is prediction and not explanation. Okay. So if the goal is prediction, the general rule or the general kind of advice is to include all input variables that for substantive reasons, so from a theoretical perspective, might be expected to be important in predicting the outcome. Okay, so that's the general piece of advice. Include everything that for substantive reasons you think is important. Of course, this advice doesn't apply when we're later on moving on to causal inference. But again, we're just talking about prediction here in this case. Okay. If you have a lot of different measures, also consider combining several inputs by creating summed or averaged total scores, right? So to the extent that certain measures are related, certain inputs are related, you don't have to include those inputs all separately, but you can add them either in an average, in a total average, or some score to combine the underlying concept that you would like to capture. Okay. Thirdly, for any inputs that have very large effects in your model building as you kind of build your model for prediction, consider also including their interactions. In general, models or inputs that have very large coefficients attached, it makes sense, at least for prediction, to include potential interactions between those coefficients as well. Okay. In all of these, of course, you have to use standard errors to get a sense of uncertainties in the parameter estimates, and always also be mindful and recognize that adding new data to your model can obviously change the estimates, and there is uncertainty attached to those estimates. Okay. Then, of course, as you kind of build a more encompassing model, essentially, you will have to make decisions about including or excluding predictors, and which predictors to ultimately include, and that should be done based on a combination of both contextual understanding, so prior knowledge about the problem at hand, the data itself, and of course, in the end, also the uses to which the regression will be put. Okay, and so in general, we want to keep predictors. After we kind of like added all the input variables in the beginning and kind of a first kind of stage that we might expect to be important. We want to keep predictors if their coefficients are estimated precisely, so if they have small standard errors, because those predictors should improve the accuracy of our predictions, and if they are important for the problem at hand, even when the standard errors are large, right? So indicators, for example, for groups that we're interested in comparing or adjusting for, right? Even if there's a large standard error attached to those coefficients, we do want to include those predictors because we wanted to include them from a substantive perspective. Okay, in that case, of course, we must acknowledge the resulting uncertainty and perhaps think about possible strategies to reduce the uncertainty, either by gathering more data or by potentially adding Bayesian priors. Okay, we can consider removing predictors if both their coefficients are estimated imprecisely, so the standard errors are very, very large, and there's no good reason from a substantive perspective for the variables to be included. Okay, so if we lack a clear substantive reason and the coefficients are very imprecise, then we can we can consider removing those predictors, because ultimately removing those predictors will allow the other coefficients in the model to be estimated more more stably and can ultimately reduce prediction errors. Okay, in general, don't automatically remove predictors because their coefficients seem to not make sense. Instead, what you should try to do is to kind of try to figure out what is going on and what is happening in the with either the sampling or the data that explains why you have an unexpected coefficient, right? So, for example, if your standard errors are very large, obviously the kind of unexpected coefficient or unexpected direction for the coefficient could be just due to sampling variation. If the coefficient is estimated precisely and is in an unexpected direction, you could think about potential reasons such as you're looking at a specific subpopulation for which the relationship is actually different than from what you expected, or other potential reasons due to the potential confounders that you included, and so on. Okay, so that's a general kind of overall strategy or guideline that you can follow to kind of build your model for prediction. In general, the strategy that we want to follow is to start with a simpler model and then slowly build up by adding predictors, and of course keeping in mind that we don't want to add too many predictors because ultimately that can lead to overfitting. Okay, so in order to kind of illustrate this using an example from the book, we'll look at the data set predicting student grades, and this is from a data set of Portuguese students and their final period math grade. And this is a larger data set. We have 343 students with their math G3 math, that's their final period math grade, and we're going to predict this final period math grade basically based on all the predictors that are included in this data set. We have a large set of predictors included. So for example, an indicator for the school, sex, age, address, family size, and so on. We have a large set of predictors, and we're just going to kind of illustrate how we work with a large set of predictors and kind of narrow down which of these predictors are most relevant, right? And we're going to kind of use this example to also illustrate the use of Bayesian priors to kind of prevent overfitting in this context. Okay. Okay. So after kind of looking at this data overview, the first thing we can do is we can just look at a basic regression using default weak priors on the original coefficient. So we're predicting student grades using all available covariates. The way we do this here is we specify only the dependent variable, and by including the dot here on the right hand side of the equation in stan GLM, that implies that we're basically using all the coefficients except for the dependent variable that are included in this data frame student. Okay, we are then just creating a plot of posterior draws for each of those coefficients. So we look at the distribution of posterior draws for each estimate. Okay, and this is the result. We have 26 coefficients. 0 here, we have a vertical bar for 0, and we have a wide range of effects. Okay, so this figure ultimately kind of illustrates that without kind of standardizing the predictors, as we discussed using kind of linear transformations, it looks like there's kind of different, there are different amounts of uncertainty on the relevance of these predictors. So for example, if we look at absences, which is the measure of a measure indicating how often the students were absent, it looks like it has very small relevance, but also very small uncertainty, but doesn't really look like a very large effect. On the other hand, we have school supplements here, seems to have a much larger effect. But of course, we can't directly compare the effect sizes of each of those coefficients because they're all measured on different scales, right? So in order to be able to make these comparisons or to make better comparisons between those coefficients and to evaluate their respective relevance in predicting success in this mathematics score, what we can do is we can just standardize our covariates, standardize our inputs or our predictors. Okay, we're just using the scale command, which automatically kind of z scores or standardizes each of those predictors except for the dependent variable. And then we're using our new student underscore z, which is now a data frame that replaces each of the original raw measures with a standardized measure. Okay. Other than that, the code is the same, and now we have a much clearer picture in terms of the relative relevance for each of those predictors. And now we see after standardizing, for example, absences, we see that this is actually much more important predictor than initially thought, because obviously the range in absences that we observe in the sample is much smaller than, for example, this school supplements or failures measure. Okay. But of course, this is a lot of different predictors, and the key issue here is that we're not only interested in predicting the outcome within our data frame, within our observed sample as well as possible. We're also interested in predicting new data sets, and so we have to be concerned about overfitting, in the sense that we're some of the results and some of the coefficient estimates in our based on this model will not help us predict the outcomes in a new data set, because ultimately they're just explaining some peculiarities of the specific data frame we're working with. Okay, so one way we can deal with this, and this is just one example that we're going to go through very briefly, is that we can make the assumption that only some covariates are relevant. Okay. And particularly what we're going to do is we will predict student grades, again including all of these covariates, but now using a regularized horseshoe prior. And the underlying idea behind this horseshoe prior is that it basically draws a lot of the coefficients towards 0. We're basically assuming that there's only, as I mentioned, a few number of relevant covariates, and all other covariates are more likely to be 0, right? Here what we're going to do is we're going to say, okay, we're assuming that approximately that there are approximately 6 relevant predictors. Okay, we could kind of as you go through this code, you can of course try this with varying numbers here for P0, the kind of expected number of relevant predictors. And we basically, what we do is we assume that that many of the predictors in the data actually ultimately have very small relevance. so the majority of them actually has very small relevance, and we want to basically isolate the predictors that are most useful in actually predicting the outcome. Okay. I'm not going to go through kind of the detail of exactly how to set up this horseshoe prior. We can maybe talk about this more in the Q&A session. But also check out the chapter in the book that kind of discusses this in a little bit more detail as well. The key point for us here is just that we're specifying basically the expected number of predictors, and we're also specifying kind of a overall kind of a scale of how much, kind of based on a prior of how much explained variance we're expecting in our outcome measure. We can also set kind of a prior on the uncertainty around our individual coefficients. Okay. Ultimately, the result of this regularized horseshoe prior is the following. We see the same plot with the same covariates, but now, as you can see, if you look at the posterior draws, or the simulated draws from the posterior distribution, that most of those, the mode of that posterior distribution for each of those coefficients is around 0. Okay, so most of those coefficients is now is closer to 0, likely to be 0, and just the most relevant predictors are actually left out, which is here: failures, school sup, so school support, we have going out, and absences. Okay. All the remaining predictors are basically regularized down to 0, right? And so ultimately, of course, this leads to worse predictive, as we will see in a second, worse predictions in terms of our in-sample predictions, but ultimately this will guard us against overfitting and will increase our predictive performance when we encounter new data sets, because we're just focusing on the most relevant predictors. Okay. We can also, just for sake of comparison, we can, as we mentioned, this regularized horseshoe prior ultimately has the benefits of shrinking the posterior for many of the regression coefficients more tightly towards 0, and that ultimately makes it easier to see the most relevant predictors. And we can now, in the next step, just focus on, in our model, just focus on those relevant predictors and have that comparison as well. There are other ways of kind of achieving this regularization. You might have kind of read or heard about, like, the lasso and other kind of similar ideas that all kind of draw coefficients closer to 0 and help you identify the most relevant coefficients. And those are all kind of similar techniques. Here we're using specific priors. The lasso is a similar technique that you could also essentially kind of represent using a certain prior distribution on your coefficients. Okay, the underlying idea is always the same. You kind of constrain parameters. You don't constrain parameters. You draw them closer to 0. And you isolate the most relevant ones and set the remaining ones either to 0 or closer to 0. Okay. As I mentioned, we can now kind of use a subset of the covariates and just focus on those. Specifically here, we're now predicting student grades using just the most relevant predictors. As I mentioned, this is failures, school support, to what extent the students go out, and absences. Again, and now we're just focusing on those specific covariates. Obviously, the next thing we want to do is we want to examine to what extent these models differ in terms of their predictive accuracy. And the first thing we want to do is we can compare these models using the Bayesian R Square. Okay. Again, we use Bayes _R Square to basically create a posterior distribution of R square values across our draws that takes into account basically the estimation uncertainty across our simulated draws from the posterior distribution for each of those models. First one, M2B, that's the model that uses standardized coefficients but with weakly informative priors. And then we have the horseshoe prior, and then we have the reduced model that just takes into account the most relevant covariates. We're just cleaning this data frame of Bayes R Square values by adding in identifiers for each of those models for plotting. And then we're plotting histograms of those posterior draws for Bayes R Square. Okay, and the result of this particular plot, we have three different distributions, Bayesian R Square, here ranging from 0 to 0.5, and we see that the weakly informative prior, including all the variables that we had, that's M2B. The first model that we looked at, of course, has the highest Bayesian R Square, so the highest kind of predictive power within sample, so to speak. Okay, and for the horseshoe prior and just looking at the subset of the covariates, we ultimately have a worse model fit. Okay, but that's of course not the entire story, because Bayes R Square here, while it takes into account the modeling uncertainty, it doesn't take into account out of sample predictive performance. So Bayesian R Square, just like the regular R Square, is still subject to potential overfitting, right? And so in order to correct for potential overfitting, what we're going to do is we're going to look at the leave one out R Square, and the underlying the underlying idea here is, we talked about leave one out cross validation. Basically what we're doing is we're going through the same steps of leaving out individual observations, and we're looking at the R square value based on the out of sample prediction. Okay, and that automatically kind of takes into account or corrects for potential overfitting. Okay. So all we're doing here is, rather than using Bayes R Square, we're using Lu R Square, which again computes the same R Square, Bayesian R Square value, but based on the leave one out cross-validation or out of sample prediction, so to speak. And if we look at those distributions of R Square or Lu R Square, we see that now all of a sudden the weakly informative prior has a much or not much smaller, but certainly clearly smaller or worse model fit or out of sample predictive accuracy than the horseshoe prior, as well as the subset of the covariance. So based on this out of sample predictive accuracy, we would prefer the horseshoe prior that includes all covariates, but basically regularizes the coefficients to make them more likely to be closer to 0, to just identify the most relevant predictors, and that ultimately gives us the best predictive performance if the goal is out of sample prediction rather than just in sample prediction. Okay, so this is kind of a summary that brings together a lot of the concepts that we talked about in previous videos: leave one out cross validation, the Bayesian R Square, model selection, and so on. So I hope this summary was useful for you. We'll talk more about this in our upcoming Q&A session, and so I'm looking forward to that. All right, I'll talk to you soon.